Unit 3 contained 2 chapters. Unit 3 was weather. Most of the weather phenomena you experience results from physical changes in matter. Differences in density cause the movement of air that you experience as wind. Heat from the sun causes water to evaporate and rise into the atmosphere. Water vapor is moved about the temperature and pressure differentials in the air, only to change phase again and become some form of precipitation. To understand weather, you had to understand phase changes and the interplays of variables such as pressure, temperature, and density. In this unit, you studied patterns among weather variables. You also studied gas behavior and gas laws to help relate the behavior of air masses around Earth to the prediction of weather phenomena. So Chapter 10 was called Physically Changing Matter. It was where we were introduced to some of the weather terms and what it meant for a change to be considered physical. What it meant for a physical change to occur. The first thing we did was just introduce ourselves. We got familiar with some weather variables, things we would find on a weather map: cold fronts, warm fronts, high pressure, low pressure, precipitation, clouds, temperature, jet stream, and the relationship between those different things. We looked very briefly at physical changes, specifically phase changes of matter. So going from solid to liquid to gas, and what each of those are called. There are 6 of them, and you should be familiar with what their names are and between what phases they are going to and from. We looked at proportional relationships. This was our introduction to gas laws, so we did quite a bit of work with proportional relationships to understand what it means for a relationship to be proportional, and we understood that if we plotted data, we would know that the relationship is proportional, like this one here. If it was linear, a straight line that went through the origin, had to go through 0, 0. If it was straight but did not go through 0, 0, 0, 0 was not a point in that data set. It was not considered a proportional relationship. In words, what it means for something to be proportional is that all of the data in the sort of X column is related to the data in the Y column by a common factor. You were either multiplying it or dividing it all by the same number, and that number was a constant. So the example here was the cost in dollars per square feet of carpet. 10 square feet was $15, 20 was $30, 50 was $75. The constant here is 1.5. So this would be a proportional relationship. Obviously, if you got 0 carpet, it's going to be $0. So it fits that definition. We were introduced to a proportional relationship by looking at how water would fill up a container. Specifically, we used a rain gauge, and we saw that any container that had parallel walls, the water volume that filled the container versus the height of water measured in centimeters or inches would be proportional. But in something like a flask, an Erlenmeyer flask or a Florence flask, the height versus volume would not be proportional, because even if you put in 2 milliliters of water every time, because you didn't have parallel walls, the water's height would not increase by the same ratio. We then applied the idea of a proportional relationship to density. And we know we've seen density before is equal to mass over volume. And here's a graph of the density of 3 different forms of water, H2O, in the liquid form rain, in the solid form ice, and then another solid form snow. And you could see just based on the line that the steepest slope means that it has the highest density, and the density decreases as we go down from ice and then to snow. Density, or the relationship between mass and volume, is also considered a proportional relationship, because the point will always go through 0, 0. If you have 0 mass of an object, you also have 0 volume. What we looked at with using density and mass volume was the idea that if we have one phase of a substance and it changes phase, something's going to stay constant, but something is going to change. What that constant is going to be is the mass. One thing we've sort of beaten with a dead horse over and over again this year was the idea of conservation of mass. Anytime matter undergoes a change, whether it's physical in this case or chemical, as we'll see in later chapters, the mass is going to stay the same because the number of particles you have are staying the same. The only thing that we would do is rearrange. So the mass of snow here is going to be equal to the mass of water, even though the volumes are different. Here you have 4 milliliters approximately of snow, and here you have 1 milliliter of water. So that would be one thing to consider if you were given a problem, let's say, where you had 10 grams of snow. And you want to find out, let's say, the volume of water that results. Well, you know when this melts, you're going to get 10 grams of liquid water. And then you would have to use the density of water, which is 1 gram per milliliter for liquid water, to find the volume. If you were given the volume of, let's say, a phase of water like ice, so let's say you were given 50 milliliters of ice, the first thing you would have to do, you can't say right away, well, that's going to melt and give you 50 milliliters of water. That's not true. The volume is not conserved because the particles are going to change their arrangement. The mass is conserved, so the first thing to do would be to figure out how many grams of ice is that. That will be equal to the number of grams of water, and then you can go ahead and solve for the number of milliliters of water using the density. So you would have to use the density of ice here, which is around 0.92 grams per milliliter. Use the density formula, find the mass of ice. That's equal to the mass of water, and then you can use the density of water to find the volume. The one thing we looked at with how water molecules arrange themselves in the liquid and solid form, it's unlike any other substance. Every other substance, when it goes from solid to liquid, the particles actually expand just a little bit. Water molecules are different. Water molecules take up much more space as a solid. You can see all of the empty space there. They form those hexagonal arrangements in solid water and ice, which is why ice floats on water, because all this empty space, the occupation of more volume, means that ice, solid water, is less dense than liquid water. When this melts, the molecules actually come a little bit closer together. Coming closer together with the same mass means you have less volume, which means that it's going to be more dense in the liquid state. We looked at an introduction to thermometers and how they work briefly. We constructed our own and saw what it took to come up with a scale. You needed a couple of set points on your thermometer to make a scale, but generally how it works is you fill it with a substance that expands when heated and contracts when cooled. So water would not be a good option for that because it does the opposite, but something like mercury or ethyl alcohol would. And the particles expand themselves as the temperature increases, and they contract as the temperature decreases, and that's how we measure it. There are 3 temperature scales that we used: Fahrenheit, Celsius, and Kelvin. You should be familiar with the conversions for each of them. So the one we used most often was Kelvin is equal to degrees Celsius plus 273. That came up a lot in gas laws. And Fahrenheit is equal to degrees Celsius times 1.8 plus 32. Now the reason we have to remember for the Kelvin scale is that if we made a plot of volume versus temperature, so volume of a gas versus temperature in Celsius, we get a linear line. So that's check 1 for it being a proportional relationship, but it doesn't go through the point 0, 0. So the math would not be very easy for us. If we want to just use a simple proportion to relate volume and temperature for a gas, we want it to be proportional. So what we do is we take this line and we shift it so that we bring it to 0, 0. We shifted it 273 units, which is where we get this conversion from, and that's really why the Kelvin scale was developed. That gives us a true 0, right? 0 Kelvin is what we call absolute 0. That's where the molecular motion theoretically of all matter stops. It ceases to exist. So we transition from Celsius to Kelvin, and we get a nice linear line through 0, 0. Proportional relationship that's going to be very beneficial when we're doing math with gases, which we will see in a bit. We introduced ourselves to the molecular motion of gases, the idea that in the kinetic molecular theory, it says a couple of things about gas molecules. They're in constant, random straight line motion, that they are all moving with different speeds. So we describe the speeds of a gas sample as the average speed or average kinetic energy because they're all moving with different speeds. They make collisions with each other and with the walls of the container. That's the only time they will change direction. And if we increase the temperature, if we provide them with more heat energy, they will start to speed up. And if we take heat away or we cool them down, the average speed or average kinetic energy will decrease. They will start to slow down and contract and come closer together. So that was our basis for our first gas law that we were introduced to, which was Charles's law. Charles's law related the Kelvin temperature of a gas to its volume. The idea that if you increase the temperature of a gas in a flexible container, that was important for this one because the volume has to be able to expand and contract. If you increase the temperature of a gas in a flexible container, the particles have more energy, they move faster and further apart, therefore increasing the volume. If you decrease the temperature, the particles slow down, contract, come closer together, and the volume decreases. The graph for Charles's law looks just like this, a proportional direct proportion, right? Direct proportion means, or direct relationship, that is one variable increases, the other is going to increase as well. Gave you a couple of diagrams to show Charles's law, just conceptually. Boiling water, particles are going to move faster, so you have a bigger balloon. If you decrease the temperature, the particles are going to slow down and come closer together. Here, because it's a direct proportion, the math, if we have nice numbers, should be pretty simple. So here's 0.5 liters of a gas at 200 Kelvin. If we increase the temperature to 400 Kelvin, we've increased the temperature 2 times, so therefore I'm going to increase the volume by 2 times. The volume is going to increase to 1 liter. Now remember, the most important thing here is that you have to use Kelvin. You have to use the Kelvin temperature because we are using a proportion. Look, Charles's law is a proportion. It's set up as a proportion, so the variables that we plug in there have to be proportional to each other. We just said on the previous page that Celsius temperature and volume are not proportional. That's why we have the Kelvin temperature. Let's try one example. Mrs. Rodriguez inflates a balloon for a party. She's in an air-conditioned room at 27 degrees Celsius. Remember, we're going to star that because I'm going to want to convert that to Kelvin. And the balloon has a volume of 4 liters. There's my initial volume. Because she's a curious and intrepid chemistry teacher, she heats the balloon to a temperature of 57 degrees Celsius, so that's the final temperature. What is the new volume of the balloon if the pressure remains constant? So they don't have to say that. They do, so that's an indication that it is Charles's law. Remember that we can always start with the combined gas law, which we were introduced to in the next chapter, but you know it now, so you can use it, and then cross out anything that's held constant because it would be the same value on either side, and you're left with the law to use, which is Charles's law. So we want to plug in our initial values. We're starting with 4 liters. The initial temperature is 27 Celsius, but do not put 27 Celsius into there. Put in 273 more, right? 27 plus 273 is 300 Kelvin. We want to solve for the final volume, so it's V2, after we change the temperature to 57 degrees Celsius, which is 330 Kelvin. The math here, because it's a proportion where you have something over an equal sign, we can cross multiply, and when we cross multiply, you get 300 Kelvin times V2 equals, that equal sign is still there, 4 liters times 330. Then I want to divide both sides by 300. V2 is equal to 4 times 330 divided by 300. We get 4.4 liters. We should have really predicted before we do the calculation so that we can make sure our answer makes sense. Afterwards, we were increasing the temperature, so we would predict that the volume is going to increase. Just looking at my Kelvin, I didn't double my Kelvin temperature, so the volume was not going to double. It only increased a little bit, so I'm only going to predict the volume to increase a little bit. So this answer of 4.4 liters does in fact make sense. The last thing that we looked at in Chapter 10 was relating the idea of how temperature affects the volume of a gas and how that's related to cold and warm fronts, and then just the cycle of how air moves in the atmosphere. So a cold front is when you have cold air that's overtaking an area, and a warm front is when you have warm air overtaking an area, a warm air mass or a cold air mass. And when those two things come together, then we have clouds to form, always. And where there's clouds, there's precipitation. A cold front here, right, would be you have warm air on the ground already, cold air is moving in, that's what's considered that's why it's considered to be a cold front. When that happens, because cold air is going to be more dense than the warm air, because if the gas molecules are cooler, their particles are closer together. Closer together means that it's more dense. The cold air is going to sink down and have to push up sort of the warm air. So you get the cloud formation to form directly in front of the cold front, right at the point where the cold front and the warm front meet. The clouds tend to be bigger, and you get to have more heavy precipitation when a cold front comes in. When a warm front comes in, that means you have cool air on the ground already, and because warm air, the particles are more spread out and they're less dense, the warm air is just going to sort of glide over the cold air that's there. It's not going to sink down like the cold front's going to do. So because the warm air just kind of rides along the cold air, you get longer, thinner clouds to form, and you get precipitation over a wider, longer area, and the precipitation is usually lighter. It's lighter and steadier. The last thing to understand is this diagram, which just shows the cycle of how the air masses heat up and cool down and the consequences of that. If air heats up, that means their particles expand more. That means that they are less dense. When they're less dense, they rise into the atmosphere. As they rise into the atmosphere, upper in the atmosphere, it's cooler. So eventually it's going to cool down. The particles are going to come closer together, become more dense, sink, and then as they heat up again closer to the atmosphere where it's warmer, it's going to expand, rise again, and this cycle sort of happens over and over again. And it's up here where we get the clouds to form, right? We saw this also more in chapter 11, so we'll cover it then in the review. But it's this process of the rising warm air that cools in the upper atmosphere. That cooling causes some of the water vapor, the gaseous water, to condense back into a liquid, and the accumulation of all of those particles, once they become too heavy, will fall back down to Earth as precipitation. And that's where we ended with chapter 10.